The second invited talk is Juhan Nam, who is an associate professor at the Korea Institute of Science and Technology. He's leading the Music and Audio Computing Lab and Music Research Group on various topics with the aim to improve ways in people enjoy, play, and make music through technology. And finally, he was also a program chair of this year's ISMIR. So I'll stop sharing my screen and it's back to you. Thank you, Johan.
Mm-hmm. So can you see my screen? Okay.
Yes.
Yes. Okay. Hi, everyone. I'm Juhan Nam from the Music and Audio Computing Lab at KAIST. I feel so honored and happy to give this talk titled Music Auto Tagging from Audio Classification to Audio Embedding. This talk is based on our previous and ongoing work that my student, Seung-han, Jung, and Jong-pil have been working. Now, Jung and Jong-pil are in industry. So music auto tagging is a task that predicts semantic categorical labels such as genre, mood, and instrument from acoustic music signals. And this is usually formulated as a multi-label audio classification problem where the output is represented as 0 or 1, where the 1 corresponds to the tags of the music. The most common approach nowadays is using a combination of audio filter bank in the front end and convolutional neural network as a feature extractor and classifier. So leveraging the advances from computer vision community, ML researchers have proposed various standard architectures so far. So early model used a one-dimensional convolutional neural layers where the filter takes entire frequency band and slide over time axis only. But many ML researchers figured out that it's good to use image classification standard architecture for music. So Choi et al. Showed so-called VGG-like architecture where 3x3 filters slide over the MEL spectrogram on both time and frequency axis is effective. Ponce et al. Investigated various musically motivated filter shape where vertical shape capture more timbre-oriented features and horizontal shape capture more rhythm or tempo-oriented features. And they show that combining all different shapes together is most effective. Lee et al. Tried an end-to-end CNN model, which takes low waveform directly as input, and they showed using a very small filter size, such as 3 samples, is key to improve the performance, and the first 5 to 6 combo layer works as log-scaled filter banks. More recently, Won et al. Proposed a compromise between MEL filter banks and learned filter banks from scratch. And they used spectrogram scaled linearly on frequency as input. On top of that, they used a set of trainable MEL filter banks, where each of the filter banks is harmonically scaled and parameters are learned through supervised learning. And it turns out that the customized harmonic MEL filter banks achieve state-of-the-art performance. And this table might Won et al. Summarized the evolution of all different CNN model in terms of retrieval accuracy on Magnatego-Tune, MSD, and MTG Jamendo datasets. And for the detail about CNN models and training method, you can check out the ISMIR tutorial on music classification presented by Means and Yane and Kunu last Sunday or Monday. They also provide online book and PyTorch and source code that they wrote for the tutorial. All the experiment, all the improvement are great, but the one of the issue is that they used a fixed number of tags in the output in the experiment. In particular, it's common to use top 50 tags, which is most frequently used in the dataset, because the tags are very noisy as they were mainly obtained from users. And also, there are high skewness in the distribution of tag. Most of all, this classification setting using like cross entropy loss between the tag label and sigmoid output of the model intrinsically assume the fixed number of class. However, in the real-world music service, a variety of words beyond the top 50 tags are used to describe a music, for example, in like playlist titles. And they include some music-specific words such as genre, but also diverse words pertaining to mood and listening context. So this brings up the following questions. Can we train the model to predict wide variety of words beyond the fixed tag labels, possibly including unseen label in the training phase? In the retrieval task, can we train the model to search with arbitrary word, like Google search? The key idea to do that is mapping the tag word to a vector space using word embedding, which is trained based on affinity of a word in a sentence. As a result, semantically similar words are closer to each other, and these similar words are far apart in the vector space. There are many available pre-trained word embedding models which were trained with different algorithms, such as word-to-vec or globe. So we can just reuse the pre-trained word embedding for the mapping. Therefore, tag words are not one-hot encoded binary representation anymore. They are regarded as another modality of input data paired with audio. Now, the CNN works as a feature extractor and provide audio embedding space, typically from the last hidden layers. And word embedding is transformed into another vector space through this cross-modal metric learning, such that positive pair of audio and tags are close to each other from each of the embedding space, and negative pairs are far apart. This idea was proposed long before and has been explored extensively in computer vision community. And one of the seminal work is device applied to image classification. In this model, the vision subnetwork was initially trained in the conventional classification settings with softmax output, and word embedding was separately trained using skipgram language model. After the independent training on both sides, the two pre-trained models are integrated through this metric learning. So we applied the same idea to music auto tagging task. So in this work, we used a pre-trained globe model for word embeddings and added an adaptation layer on top of that. And we used triplet network where the audio is used as an anchor and the tag label of the audio as a positive and random selection of non-labeled the tags as negative. So once the training is done, we can project any audio or any word into the co-embedding space and find the nearest items for music annotation and retrieval. So this enables so-called zero-shot learning. So on the left side, it shows top 10 nearest tag for a given audio. And the only the seen tag, but also in the training set, but also unseen tags, which do not exist in the training set. For example, Stevie Wonder's Superstitions, top 1 prediction is funk. This is unseen tag, and this prediction quite makes sense, right? On the right side, it shows a top 5 retrieved audio track for unseen word. For Lovely as a query, retrieved songs are mainly 1950s oldies goodish songs and some jazz music. This has some bias in old pop songs, but it generally makes sense. And another observation is in the transformed word embedding space. On the original word embedding space, the top 10 nearest word to the lovely include awesome, cool, romantic, relaxing, and so on. But after the space is acoustically informed by the metric learning, top 10 nearest word to lovely include like love songs and easy listening and ballad, which are more like musically oriented. And this work by one author took one step further and used domain-specific word embedding. They trained word embedding from scratch using a tokenized 100 million word corpus from Sam Evel 2018. The text corpus contained Amazon review, a music biography, and a Wikipedia page about music theory and genres. And they showed that the domain-specific word embedding captures musical context very well. For example, for jungle as a query, the nearest word in general word embedding include like rainforest, Amazon jungle, or swamp as a geographic place. But in domain-specific word embedding, understand the jungle as music genres. So it retrieve breakbeat, dub, drum and bass, and so on. In addition, the domain-specific word embedding include music diagrams such as deep house, smooth jazz. However, they report that domain-specific word embedding did not help increasing the performance in the retrieval task. Okay, so now we can allow user to use any word as a query using the cross-modal metric learning between audio embedding and word embedding. However, a practical issue is that it's difficult for user to conceive appropriate word as a query. Say you are imagining some song that you want to listen to. Drawing some word that catch the characteristic of the songs is not trivial. To tackle the issue, query-by blending by Watanabe and Goto proposed to add artist ID to the word embedding. So in this method, they represented audio song with a sequence of audio word using K-means clustering on MFCC audio features, and they obtained text word from lyrics, and also they used artist ID as another word. Therefore, a single song has a set of words from lyrics, audio, and artist ID, and they form a sentence. Then they applied the word-to-vec method to learn the blended word embedding. So what's nice about this approach is that audio and word and artist ID are all on exactly the same embedding space. Therefore, like addition or subtraction arithmetic is semantically applied to the retrieval. For example, if a user use multiple query with plus sign, the system displays songs similar to the blended flavor in 3 different aspects. And also, if the user use multiple query with minus sign, the system removed the song with the flavor of the negative query. Okay, we also tried to customize the word embedding. The difference from the previous work is that we used a wide spectrum of corpus in terms of musical specificity. So most general corpus is Wikipedia, which is frequently used to learn the word embedding in NLP. And next corpus is Amazon music review from the MuMu dataset. And it has musical context, but the texts are mostly album level and containing personal opinions. all music data set contain 4 types of tags for each song. And theme and mood are related to listener's context, and genre and styles are related to song attribute. And this is definitely more music specific than the music review data. Finally, we used artist and also track ID as a unique word. They are most music-specific words because they are used as a metadata of the song. And we recently updated the musical word embedding by adding the last FM tags. So this is the statistics of the general and musical corpus. A notable thing is that each of the data set has a large number of tokens. In general corpus, all tokens are from word. In music review, the majority of tokens are from word, and a small number of tokens are from track ID and artist ID. On last FM in all music data set, majority of tokens are from track ID and artist ID, and small numbers are from tags. Finally, we combine the review and the tags, metadata all together into music corpus, remove all redundant tokens. So as a result, overall, the music corpus is about like 14 to 15% of the general corpus in terms of volume of unique token size. And we train the word embedding by sampling positive and negative pairs from 3 different combinations. The first is word-to-word pair, which are sampled from Wikipedia and music review. And the second one is word-to-tag pair, where words are sampled from Wikipedia and music review, and tags are sampled from all music and last.fm tags. The last one is word-to-metadata pair, where the words are sampled from music review, and metadata are from the MSD, the artist and track IDs. Since the word dictionary is shared across all data set, the general word become more like musically informed. So after the training, we can measure how two words becomes closer or far apart. So between electronic and club, the two words has about 0.198 cosine similarity when the word embedding is trained on Wikipedia. On musical word embedding, the cosine similarity of two words dramatically increased because electronic is music genre and played a lot in music club in music context. Between yoga and relax, the musical word embedding tended to boost the similarity, which makes sense. Between yoga and energetic, which somewhat like contradictory, musical word embedding tended to attenuate the similarity, which also makes sense. So our original motivation of the musical word embedding was bridging the gap between listening context and music. So we used 2 music genre terms here, electronic and house, and 3 listening context terms, club and club dance and partying as a relevant word. On Wikipedia, the gap between terms are significant only between house and club. But in music corpus, the 2 genre terms, house and electronics, and also club and club dance are tightly clustered, while partying is significantly beyond the cluster centroid. But when Wikipedia and music corpus are combined, although partying is still outside cluster, but of the all other terms, it's substantially closer than the music corpus. So this indicates that using both general and music-specific word has potential of capturing more balanced correlation between music and the listening context. And we conducted cross-modal metric learning between the audio embedding and the musical word embedding that we trained. So in this experiment, we generate the triplet samples not only under supervision of tags, but also the supervision of artist and the track. In other words, the anchor positive pair can be chosen not only from audio and its corresponding tags, but also the audio and its artist ID, and also the audio is the track ID, because artist and track ID are also regarded as a word. As a result, we can have 3 terms of triplet from tags and artist and track supervision. And this is possible because the musical word embedding include tags, artist ID, and track ID all together. So in this experiment, we compared the pre-trained globe embedding in the zero-shot learning model that I mentioned before to the musical word embedding by replacing only the word embedding part. In addition, we tried 3 different algorithms, globe, CBOW, and skitgram, to train the word embedding, musical word embedding. And it turns out that the musical word embedding worked better than the pre-trained globe for both annotation retrieval when skitgram is used. But when globe and CBOW is applied to musical word embedding, the performance become actually lower. We also compared different combination of supervision in in the annotation task. The blue group tag supervision works best. This is probably because annotation task is more relevant to the tag supervision in terms of musical specificity. In yellow group, a combination of tags and artists works best for the same region, and accuracy is higher than that from the tag supervision only. Finally, when tag and artist track supervision used all together, model achieved the best accuracies. In retrieval task, the trend is different. In the blue group, track supervision worked best. This is probably because the retrieval task predict tracks, which is more music specific than the tags. In yellow group, a combination of artists and tracks works best for the same region, and accuracy is slightly better than that from the tag supervision only. When tag and artist track supervision used all together, unlike annotation task, accuracy is not the best. This is probably because tag supervision kind of weakened the musical specificity. In the retrieval task, we also evaluated KELF 500 and Jamendo as a test set. In zero-shot experiment, we used only nearest neighbor and used the 2 data set in unseen scenario. And linear proof, we fixed audio embedding and trained only the top sigmoid layer with the training split of KELF 500 and Jamendo. And both experiment using tags and tracks provision here, or using all of them generally works best. But in the linear proof, artists and tracks provision is also comparable to them. Okay, I'm almost done. And my student Seung-won implemented a web-based music search system using the musical word embedding, and that was introduced in the late-breaking demo yesterday. Let me just briefly play the short demo video.
So we can search by the mellow R&B, like this type of vertical rate. Never the same chord like a forest.
Yes, this shows the demo that you can type any word that you can imagine to retrieve music.
So
So okay, it's time to wrap up my talk. So here's the takeaway message from my talk. The cross-modal metric learning can expand the music audio auto-tagging task to learn co-embedding space between an audio and text. And the musical word embedding trained with wide spectrum of corpus can bridge the gap between listening context and song. Finally, musical word embedding is more flexible in handling different musical specificity of supervision, like tags, artist, and track in the cross-modal metric learning. Okay, that's all I have. Thank you for listening to this talk.